Hey everyone, Mr. King here. Today we're going to talk about the structure of matter, and we're going to basically be talking about what everything in the universe is made of. Matter is anything that has mass and takes up space, and that's going to be almost anything in the world that we're talking about. Examples of matter are you, your science binder, a book, anything you can see or touch. Take a look around the room you're sitting in right now. Anything that you can see is matter. If you can walk around and touch it, it's matter. So you might think that includes everything and anything, but it's not. There are some things that are not matter. Your emotions, your thoughts, your ideas, those you can't reach out and touch. Another tricky one is light. Light is not matter because light does not take up space. If you turn the lights off in the room you're sitting in right now, it's not like there became more room for you to move around. Light does not take up space, so light is not matter. Heat is another thing that is not matter. Now the air is matter, and this is where it gets kind of confusing. Air is matter because if you take your hands and do this right now, wave them in front of your face really fast, or take a piece of paper and wave it in front of your face, you're fanning those air molecules towards your face. So those can actually be touched because you can feel them on your face. They can be moved. Now heat is that idea that there's the kinetic energy. If you remember, we've talked about this a little bit. The temperature increases because things are banging into each other more. So when we study the states of matter, when the liquid, when you put heat on it, it turned into a gas because it started to have more kinetic energy. It started to have more movement, and that created more heat. Now heat, you can't reach out and grab, you can't reach out and touch it, but you can feel it. And so you might think, no, that's got to be matter. Well, what you're actually feeling is the air that has been heated. So the air particles are moving faster. So air is matter, but heat is not. Okay, so that one's kind of tricky, but everything else is pretty easy. Like I said, anything you can see or touch, that's matter. Things that you cannot, all the thoughts in your head, things like that, those are not matter. So this guy named Democritus, you can see a great looking picture of him here with some sweet curly hair. He is the first guy to come up with this idea that everything in the world is made of these tiny little things called atoms. Now this was a long time ago. This was back in about 370 BC. So we're talking over 2,000 years ago. Democritus had this idea that if you broke down everything in the universe to its smallest piece, you would find this thing called an atom. And there is no way you could divide it any smaller. So the smallest thing in the whole universe is an atom, and it can't be broken down any smaller. Now this is what he thought. This is not true, but this is what he thought back in 370 BC. And at the time, you can imagine people might have thought he was a little bit crazy. You can imagine him sitting around going, "Hey dude, check this out. Everything in the world is made of these tiny little things that you can't see." And everyone said, "Democritus, you got to be crazy to think that." But he was actually right. But at the time, no one believed him. Everyone kind of thought he was just this crazy thinker who didn't really know what he was talking about. Along with this idea about matter is the law of conservation of matter. And we've talked a little bit about the law of conservation of mass. This is the same thing. Matter is neither created nor destroyed. It only changes form. Like I said, it's just like the law of conservation of mass. But matter is anything that has mass and takes up space. So it has volume. So that makes it a little bit different. You see a picture of this guy down here. His name's Antoine Lavoisier. He was the one who came up with this bonfire example that we've talked about, where if you burn a piece of wood, you're left with ash and smoke that is equal to the amount of matter you started with. So if you could somehow capture up all of that ash and smoke and put it on a scale, you would have the same amount of matter that you started with that wood was made of. Before Lavoisier, people used to think that matter could appear and disappear. I have the caption here, "Looks like magic," and I've told you guys, magic isn't true. You really can't make things appear and disappear. It's just an illusion. And so all of the matter in the universe stays the same, the total amount. It just changes form. That's the only difference. So we talked about Democritus back in 370 BC. People basically did not touch the idea of atoms until this guy, whose name is John Dalton. He was actually a school teacher. This was about the early 1800s. And John Dalton came up with this idea that everything that you see is made up of atoms, but the atoms are too small to be seen by the human eye. And this was very similar to what Democritus thought. His theory of matter, Dalton's theory of matter, was an idea model. Okay, if you remember, we've talked about the three types of models: the physical model, the computer model, and the idea model. This is the idea model. So that's one you can't see or touch. It's just a set of thoughts. And so he also took Democritus' idea about everything being made of atoms. He took it a little farther. He said each type of matter was made up of only one kind of atom. So for example, if you had a piece of gold, that's just made up of little gold atoms. And this kind of makes sense. In order for something to be a large piece of something, it has to be made of a bunch of small pieces of the same thing. So Dalton kind of took Democritus' idea and advanced it, and people finally realized that Democritus knew what he was talking about. He was a pretty smart guy for his time. So these atoms, how big are they? They're too small to be seen by the human eye, so you and I will not see atoms floating around or anything like that. Each type of matter is made of only one kind of atom, and 1 million atoms lined up in a row equals the thickness, not the length, of one piece of human hair. They are tiny. So it doesn't matter how long your hair is. If you yanked out a strand, we're talking about the thickness, okay? This very, very small amount. You can line up 1 million atoms and set them on top of each other. And that's about how big it would be. So these things are super, super tiny. I'm going to show you a little video here about the size of atoms. And this is pretty cool. It's kind of crazy to think about how tiny they are, but this will kind of put it all in perspective for you, I think.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? That's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms of the mass of an atom is in the nucleus. Now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. Now let's go and grab all of the nuclei from a typical car. Now cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, you would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
Alright guys, so you can see an atom is just super tiny, and we're going to talk more about the size of an atom, and we're going to talk about the protons and the neutrons and the electrons and the nucleus with our next lesson, but this gives you an idea about the size of these things. They are so small, it's hard to even imagine. So we'll talk a little bit about that more next time. I hope you guys have a great night. Write some great questions, do well on the quiz, and I will see you all tomorrow.